move into introducing Dr. Robert Stewart, who has a PhD in chemical engineering from the University of Alberta and a BSc in mechanical engineering from University of Waterloo. He has worked on energy storage technology and project development for the last 7 years. His career ambition is to develop and implement energy storage technologies to support renewable energy generation integration. Currently, his focus is on long duration storage assets and associated innovative business models. He does have a background in technical support for oil and gas machinery, including industrial gas turbines, with a focus on performance monitoring and risk-based maintenance strategies. So with that, I would like to hand over to Robert and let him take it from there. Thank you.
Great. Well, good evening, everyone, and thanks very much for having me this evening. I'm looking forward to sharing what I and my employer, RMP Energy Storage, have been up to, and specifically a white paper that we've recently released. I'm open to any questions you have now, and I'll share my email at the very end of the slides for those who may have questions come up later. So with that, I'll share my screen here and dive right in, I think. There we go. So as I said, I'm working for RMP Energy Storage, and today I'm going to present full-time zero carbon electricity with compressed air energy storage. So these are just some highlights that I'll cover in detail through the presentation, but just to sort of whet your appetite. So CAES, you'll see it a lot, it's compressed air energy storage. Right now, what the white paper shows is that we can deliver low costs and low emissions dispatchable power at a competitive price with combined cycle gas turbines, or CCGT, using CAES and wind generation in Western Canada, with an opportunity for zero emissions electricity. Building facilities like this will employ hundreds of skilled workers directly from oil and gas backgrounds, everyone from drillers, pipe fitters, engineers, geoscientists, geologists, financials, and landmen. Everyone in the current space will be directly transferable to this technology. Right now, there's $2.5 billion that's been set aside within the Canadian Infrastructure Bank for storage and interties, and we're aggressively trying to pursue this to have something deployed within Western Canada utilizing this funding. RMP Energy Storage has been working on compressed air energy storage for over 8 years. Right now, where we are is we've got a $5 million requirement for the next stage of development, which includes front-end engineering and design. CAES is a proven technology. Right now, you can build an asset with more than 15 times the duration for the same capital cost as a lithium-ion battery. Alberta and Saskatchewan have the world's best and known geology for this technology. And we also have the expertise that can be transitioned directly from oil and gas to build them.
Which took all our numbers down. And also, normally we...
So who we are? We're federally incorporated. We've been around since 2006. Originally developed the Montana-Alberta tie line as Rocky Mountain Power. We recently went through a corporate name change to elevate the focus of storage to the front of our name. But we have been involved in tie line development, wind power development, solar development, and even pumped hydro development. We're technology agnostic with strong roots in Alberta and Saskatchewan. And you can see on the right there some of the projects that we're looking at the compressed air energy storage projects fit within the saddle, or the Saskatchewan Alberta tie line company. So I'm going to take it really back to basics here for everybody. So give me a moment. Hopefully we get everybody on the same page, and we'll be able to move forward with some of the rationale for why we're so focused on energy storage in a minute or two. So way back to basics. Consumers are demanding more renewable energy. You know, this is driven by many things that we see every day in the news or we observe in our real lives. Increasing wildfires, floods, droughts, potential sea level rise, etc. We're inundated with this message from media, and investment is now moving in these directions. Really, consumers are driving this by saying we want to buy green products, we want to vote for climate solutions, and at the same time, corporations are moving to align with this so that they aren't stuck in the past. This demand for renewable energy actually creates a lot of challenges for the grid and a lot of opportunities for those who can solve them. So if we look at demand, electrification gets thrown around a lot. What is it? Electrification is effectively transitioning from one fuel source to electricity as your primary fuel source. That could be in road transportation, buildings, heating and ventilation, and industrial processes. This is occurring throughout all major sectors because of the reduction in electricity and the rise of cheaper, better power electronics. It enables us to use energy more effectively and cleaner. And an example of how this is, one part of this is going to impact our lives is that one electric vehicle will more than double your electrical demand and increase your consumption by over 50% at an individual house. So you look at every house on your street, you start to think if everyone had an EV, or one in even every 5 had an EV, this starts to be a really big demand change and also demand on the grid. So looking at the other side of this, we look at supply and we say, well, where is this additional electricity coming from? And we see that renewables, this is now a year old, this slide, these numbers have actually come down. And renewable energy is now competitive with thermal generation, not only in building new assets, but in fact, it is now competitive on an energy basis with existing facilities. So that's fantastic. It's got no emissions, so it checks off the green box. It's got no fuel input, so you have reduced the cost exposure of that facility to increases in the future. But one of the issues is that it's not dispatchable. So this energy is not, or this electricity that's being generated by primarily wind and solar assets, it's not available on demand. And as a consumer, when you think of electricity, and one of the reasons we see such drive towards electrification is that electricity is always there and it's very reliable. So as we shift to using more electricity, if our supply becomes not dispatchable or less available, this can cause a lot of challenges. One thing I want to note is that these prices are in US dollars and they're put through by a company that revisits these numbers every year. We've seen prices below the number for wind in Alberta and Saskatchewan in the recent RFPs. And in the solar, I know that we bid projects that are below or within these bands within the provinces. So these are realistic numbers, and there's data to back that up. One of the very unique things about electricity and generation in particular is how every jurisdiction is unique. Every jurisdiction has their own method of having customers pay for electricity. They have their own method for generation sources being dispatched, and even generation sources being determined which will be selected and built. So in Alberta, we have an open electricity market from the generation perspective. What that means is that all of the generating assets within the province are owned and operated by public or private corporations. It's not directed by a central planning organization. So anyone can build, provided you follow the rules. And that means that we have a great opportunity to be able to change what's in the market and what's delivering our power. And we just have to take that opportunity. Saskatchewan is a vertically integrated crown corporation called Sask Power. And as you move across the country, there's multiple different scenarios that occur. Obviously, this causes challenge when trying to integrate new technologies and new business models, because you have to recreate that model in every jurisdiction, not just based upon the resources that are available, such as cheap gas or lots of hydro, but also how do you develop a facility and how do you then implement that into the market. One of the interesting things about Alberta is we're currently undergoing a massive supply change. So by 2030, Alberta will phase out our coal plants. As you can see up there in black, right now it's making up 5,500 megawatts of our generating capacity, and it delivers over 40% of our electricity. This is a massive change. And one of the opportunities we have is to replace that with renewable generation like wind and solar. As I said, this isn't directed by anybody. We need investment to take place and investors to take on the opportunity to deploy these types of assets. And one of the challenges, of course, we have is that these are intermittent assets. So how do we ensure that they are generating the sort of revenue that we need to be able to have them participate in the market? When we look at the opportunity in Western Canada, we're very blessed, and Prairie Canada in particular. We have high average wind speeds and we have high solar output compared to the rest of the country. Really, this means that we can get better energy production for lower prices than we would see elsewhere in the country. And it really enables us to push forward with these as our primary sources of energy should we want to. We also have a large amount of land that is suitable for these developments close to our load centers. So I've alluded to this, but the situation is that renewables are really cheap. That's great. They're emissions free. That's awesome. They're fuel free. That's also awesome. And they're intermittent. You look historically at how the electrical system has been designed, and it's really quite dissimilar from a lot of other fields where we have generation meeting supply in real time. Is that a question? I'll move on.
I didn't. Well, I thought I saw your photograph there.
Sorry, I think we should go on mute if we can, unless we have a question.
You want me to send it to you?
So when we look at the electrical system, it's been really designed with generation.
Sorry, Robert, I muted you. Can you unmute yourself?
I think so. Can you hear me? Yeah.
Yes, thanks. Yeah.
Perfect. Okay. Thank you. So when we look at other spaces, we have storage is used in all other spaces to allow supply to meet demand. When supply is greater than demand, you put something into a warehouse, you put it into a water tower. When you need it and demand is higher than supply, you're able to take it out of those warehouses, out of those storage assets. This is really not how the electrical system has been designed. Of course, when you have pondage in hydro, that is kind of a form of energy that you can dispatch, but it isn't really taking it from electricity and putting it into storage and then taking it back out as electricity. So every jurisdiction is unique, and we think that we have this sorted out for Western Canada. One of the questions is, well, how much storage do you need, and what is the cost? So now I'm going to take a little bit of a sidestep towards the technology that we've been focusing on, and then we'll go through the modeling and get to why this is really the technology that makes the most sense in Alberta. So compressed air energy storage is proven. It has long duration capabilities, well over 24 hours in duration. It uses the same type of equipment that's already used in hydrocarbon storage facilities. Subsurface caverns are purpose-built through methods such as solution mining. Saskatchewan and Alberta have ideal geology for this type of cavern construction and disposal, as has been proven by decades of oil and gas use. There are 2 long-term projects that have been in operation for over 70 years of combined operation in Alabama and Germany. And the major equipment suppliers include your laundry list of top-tier equipment suppliers such as Siemens and GE, MHI, etc. There is other projects ongoing in Canada, including CAES, which I'll get into, stands for adiabatic compressed air energy storage, a pilot and a demonstration in Ontario, and development continues in this space globally. When we look at these 2 facilities that are operating, the first of which was commissioned in 1978, they're currently still operating, and they're considering an expansion, is the latest word I've heard. There are 290 megawatts of generation capacity. The second facility was commissioned in 1991, and it's 110 megawatts in capacity. Now, both of these assets were built for a different purpose than what we're proposing compressed air to be used for, and what it's being looked at by others today. These 2 assets were really built to manage fluctuating load when the supply or the generation was inflexible. So you have a large nuclear facility or a very large thermal fleet that is inflexible in its operation, or it desires to operate at one set point. These assets were used to manage that generation and manage that load. So the difference is today we have fluctuating generation and fluctuating load. So you're still dealing with the supply-demand imbalance, but you're not controlling either side, and that's really where we're trying to utilize this technology again. So when we go into a little bit more detail on how CAES works, when you're charging on the left-hand side of this diagram, you take electricity from the grid when it's cheap or it's from the contracted source. It runs air from ambient conditions through a series of compressors. Heat is rejected from compression, and then that air is stored in salt caverns underground. These salt caverns are specifically designed and built for this purpose, and are very similar to the natural gas storage caverns that we have today. Really, the size and pressure of that cavern dictate how long you can run the expander and compressors for. So that gives you your duration. When you want power out and you're discharging the asset, you take air out of the cavern and you add heat back into that air and you expand it out and drive a generator. So you can see it's a fairly simple process. The schematic and the mass flow is pretty simple. but the operation of the asset is slightly different from others that we might see where we're operating charging and discharging components at different times. So I spoke about adiabatic compressed air energy storage. There's really two types of ways that you can add the heat back in during the discharge stage. Diabatic compressed air energy storage uses a secondary thermal source, so natural gas is one example. And adiabatic takes the heat that's rejected during the compression stage, stores that externally, and then brings it back in when you need it to reheat the air. So you can think of diabatic or CAES as like a hybrid car where you're able to take some electricity in from the grid or from charging during braking, but you're going to supplement it with some form of fuel, and that allows you to get more electricity out than electricity that you put in. With the adiabatic compressed air energy storage, of course, this is more like an electric car where you're charging from the grid and you're discharging to the grid. There's no external additional energy source, so you're always going to be putting less energy back onto the grid than you put in. So one of the questions we get a lot is, well, how does this compare to batteries? I hear about batteries all the time. You know, lithium-ion batteries are always in the news. You know, that Elon Musk guy is always up there at the top of the media feed doing something amazing. So, you know, how does this compare to batteries? So let's just run through how batteries work from an energy storage and a grid energy storage perspective. Battery cells are roughly 50% of the cost on a CapEx basis for a 1-hour battery. And the duration that you can operate that battery for would scale linearly with the number of cells. So that means as every additional hour of duration you add on, you're adding an additional 50% of that initial investment for a 1-hour asset. With the compressed air energy storage facility, your CapEx increases very little with additional duration. And the reason for that is because all of the costs associated with building the caverns are an upfront single cost. You basically drill an additional well and pump water for another 2 years to build an additional cavern. And an additional cavern can give you significant more duration. And what that results in is doubling the duration of a diabatic compressed air energy storage asset from somewhere like 30 to something like 60 hours. It costs you less than 6% additional CapEx. So therefore, where geology permits, compressed air energy storage really aligns well with long duration storage needs where you can add that additional duration very cheaply. And that really supports the integration of renewables. Batteries are fantastic for short duration events such as frequency response, peaking load demand, or some transmission constraint reduction. And these are really providing complementary services. So when we look at Western Canada, again, we have the skills. You've now seen how this technology works. You know that this is very similar to how many gas facilities operate, whether it's a straddle plant or just a compression station or a storage facility. We have the skills within Western Canada to build these assets. One thing that many locations don't have is the data to show that the geology is real. This is a huge value that Alberta and Saskatchewan have, and that's the public domain well logging data and cores that have been collected over the last decades of oil and gas exploration and production. And this is a resource that we can utilize in reducing the risk in the development of compressed air energy storage projects, which allows us to develop these faster and cheaper than other locations. We're also very lucky to have ideal geology. So the depth and the thickness of the salt that you are building these caverns in is really important to the operation of the facility, as its efficiency, and also the stability of the formation. And we're very fortunate to have salt that is at the ideal depth of sort of 800 meters to 1,500 meters for this sort of development. Finally, we have great wind. You saw that on the map that helps us generate lots of power easily. And then we have this market opportunity where we have a large change in the supply occurring right now. So this is just showing you the salt deposit in Western Canada from one perspective. One thing that we also have is the ideal ability to dispose of brine. So this is something that you don't find in Eastern Canada, in many parts of Europe where there are salt deposits. It's very hard to get rid of the brine that is produced when you solution mine a cavern. We're very fortunate to have the geology that can provide the water, the brackish water for doing this, and then also provide the disposal location for that saline water. And this is critical in understanding why this technology is well suited for Alberta and Saskatchewan, and also why we haven't seen it uptaken in places like California or places like New York that maybe have very stringent mandates on renewable integration. They simply do not have the geology to do this. So that brings us to sort of the question of how much does this cost? And while we've done an awful lot of modeling on historical costs within the Alberta market, and we can prove that this sort of asset would make money, the question remained of how much storage is really required along a certain amount of renewable energy. What is the right ratio? What duration do you need? And then from that will spit out a cost. So what we did was we did a bookend analysis. This is really looking at if we wanted to go to a nearly 100% or a 100% renewable system, how much storage do I need to do that? This could also be considered as a firm renewable product. So should a Google or a load-heavy customer want to have electricity 24/7, 365 that's all renewable, how much does that cost? What sort of size asset do you need to do that, or duration asset do you need to do that? So this analysis is useful from two perspectives. What we did is we used historical hourly load data and hourly wind generation data. It's important to use historical data because they capture real events and real cycles and how they align within the market. We then modeled diabatic case, adiabatic case, and lithium-ion battery operation to enable, in this case, wind generation to meet the load. We then compared different additional wind and different additional storage numbers to determine what the levelized cost of the entire system was to deliver energy to that load. And then we compared those to determine what the cheapest or most optimal scenario was. So I'll just go through quickly. I won't go through this in detail. This is some of the input data that we used. We used 2017 Alberta overall load data. Alberta is unique. It does have a very high load factor, so these numbers would be different should you move them to other locations. And we used wind data from the facilities that are below. So we used Wintering Hills. We used 2 years of data from Wintering Hills. We used 1 year of data from Bull Creek, and we used Bull Creek. It's a smaller facility, but it's also one of the newest that we have a full year of data for. Excuse me. And then we used the entire Alberta fleet and used that as one of the inputs. So you scale all of these to the same size and then increment that size within the model. And then we blended a fleet of Bull Creek and Wintering Hills. And what that really allowed us to do was look at, does the location of your wind matter? And is it better to be co-located with a single wind farm or is there benefits of, or what are the benefits of charging from multiple wind generation assets? Up above are a bunch of numbers. We looked at two different efficiencies for compressed air energy storage, or the adiabatic compressed air energy storage. One at 50%, which is I think on the low end, but is 100% achievable. And then 65%, which is probably pushing the upper end of what's thermodynamically feasible. And then the adiabatic case, again, it's not really an efficiency here that's 145%. It's that the megawatts of electricity that are output are greater than the megawatts of electricity that are input, because you are supplementing with 3.8 GJs of natural gas per every megawatt hour that's output. So it's more like a hybrid car. So this changes the costs. We then ran the costs at different IRRs and looked at how did that make a difference to the system. One thing I will note is that newer turbines that have higher capacity factors than what are shown here have been installed in the province. And so we'll start to see some new data from those for a full year, sort of in the next couple months. And that'll be very interesting to see how that is different. These capacity factors are very good. Globally, these capacity factors are amazing. But with taller turbines, newer turbines, you're going to get more production more of the time than you would with these, now 8-year-old, 9-year-old turbines, or with the Alberta total fleet, even older than that. So just looking at the wind data, one thing that's important to know is that wind generation across the province is highly correlated. So there was a study done by the Alberta Electric System, or for the Alberta Electric System Operator, the ISO, that showed that on an hourly basis, we've got an R-squared value greater than 0.5, so quite high correlation. On a daily basis, it's even very high. And obviously individual wind farms, because they were all clustered, all the turbines are clustered together at a single location, they're all generating pretty much at the same time. And you see that in these plots. You see this Bull Creek, which is a smaller facility. It's basically on or off. And then Wintering Hills has a bit more shape to it. But then the all Alberta numbers are much lower in terms of their volatility, but they're all showing the same sort of shape. You get low periods and they're all low, and then higher periods and they're all higher. And so this is a problem when integrating wind generation into the province, because all of your wind is following a similar pattern, and particular during certain periods of the year, we end up with not a lot of wind farm, or not a lot of wind energy coming through the province. So this is a bit more on the operation of the model. It runs through on an hourly basis. The storage asset does not have any foresight in what is coming in the next hour or the next week in terms of wind generation. So it's not optimized. And that's really important to know, because you can optimize these models so that you end up with a much smaller storage asset than you might need in reality. We then run through and see what groupings of sizes of storage asset and sizes of wind farms meet the load. So our load has no unserved hours. All of the load is served. The cost of the actual scenario is based on a wind energy input cost and the storage asset cost. And when looking at the wind energy, while some of the energy does not go into storage and does not go to the asset, it is paid for in the model. So it's effectively being wasted, but it is accounted for in the model, because you're saying, I'm going to buy all of your output wind farm, and I ascribe, a dollar value to everything I buy, but I'm not going to be able to use it all. So in an actual system, that would have some value, and that's not accounted for in this model. So it's conservative. There's also no value for carbon ascribed. And so you can assume that if there's a value for carbon that you would sell a credit for, it would further reduce the costs that we see in the model. So this is a graph showing all of the hours in the model from one specific case with one specific wind farm size and storage asset size as an example. So what you can see is in red, that's the load. It's around 20 megawatts it peaks at, and it's being met all of the time by the wind generation facility, which is much larger than the load. It's probably 88 megawatts or 90 megawatts. And then the storage asset, which is a 20 megawatt storage asset. And so this, in this case, an adiabatic compressed air storage asset. And then the yellow line is the most interesting line to me. So that's aligned with the graph on the right, and it's the state of charge. And so that's basically, is this thing 100% full, or is it at 0% full? And what became really interesting through the modeling exercise was that these lower wind periods are what are driving the requirement for along a certain duration of the storage asset. And when you look at the trying to provide a load with power 100% of the time with the renewable and the storage asset, this duration is really driving the cost of the system. This asset, as long as you have the duration to get through the largest gap, the efficiency doesn't matter significantly. And that's because you're able to charge at some other point and make up for it, but if there's no opportunity to charge in this low period, it doesn't matter what your efficiency is. So you could have a battery that's 100% efficient, and it would not change this duration significantly because the amount of electricity being generated by the wind asset is so much less than what is being demanded by the load during that period. And I thought that was really interesting, and it aligned really well with what we saw in the economic models with looking at this from a merchant facility, where you basically say during high wind generation periods, the pool price effectively goes to zero. So your input cost is effectively zero. And what that means also is that your efficiency doesn't matter, because you can buy that energy for nothing. If you're throwing half it away, it doesn't matter. What matters is, do you have energy when the prices are high? So prices are high during this period right here. That's kind of the analogy. And that really pushes us towards compressed air energy storage versus a lithium-ion battery technology, because the cost of that additional duration is so much less. So this is a highlight of the outputs from the study. This is pulling after-tax IRR of 8% for the compressed air energy storage facility. Our baseline used $45 per megawatt hour for the input wind, or the purchased wind generation. We already know that $30 per megawatt hour is possible. We think that SaskPower has likely received bids in this range. And what this results in is a price range of sort of $89 to $70 to $89 in terms of electricity being delivered to the load with a diabatic compressed air energy storage facility. With an adiabatic compressed air energy storage facility, so again, no thermal input, no natural gas input, our cost goes up a fair amount because it's a significant amount of additional wind energy has to be purchased for every unit of electricity that's regenerated. And you can see that delta decreases significantly when you reduce your wind input cost. but it's still quite a bit more expensive. Initially, when we ran this, we were trying to see how much a 100% renewable product would cost. And then we ran the diabatic compressed air energy storage because we had the numbers and we could do it. And what really surprised me was that the actual emissions output from that blended number was very, very low. So while the diabatic compressed air energy storage facility uses natural gas, because you're using that asset so much less than you would a combined cycle gas turbine to meet a load, you are more than 80% lower on your emissions from the blended product than you would be from the combined cycle gas plant delivering the same product. And when you look at the cost range, when you consider a reasonable range for the outlook of natural gas within the province, you can see that they're at the high end, they're not that dissimilar. And if you look at a 25 or 30 year asset, not considering the carbon cost, you're in a good place with the adiabatic or with the diabatic compressed air energy storage facility and wind generation. And so that became really a very interesting outcome from this study that I wasn't expecting, was to see that my thought of we need to get to 100% renewable, so we have to use an adiabatic compressed air energy storage facility. Well, if I can get 80% of the reduction compared to a combined cycle gas turbine, which is very much lower than a coal plant, we're not that far off in terms of cost. And so to go to 100% renewable product, to get that last 20%, you're adding a significant amount of additional cost. And while some entities may want to be able to say they have zero emissions, saying that you're 80% below the best-in-class gas turbine with today's technology, like we can build this today, that was astounding to me and very exciting. So that's the thing that I want to really impress upon people, is that we can provide, we can develop a project today using today's technology at a competitive price with much, much lower emissions than a combined cycle gas turbine. Cognizant of the time here, I want to leave some time for questions, but I wanted to touch on this co-location topic just briefly. And this goes back to the correlation of wind generation within the province versus within a specific wind farm. And what I found interesting here was the costs that we were seeing out of the modeling. The lowest numbers were always the blended, the two wind farms blended together, or the all Alberta wind farm fleet charging. And that was interesting because the Alberta fleet has a lower capacity factor than individual wind farms that we were looking at. And what this came down to was that while the correlation is high across the province, the fact that it's not 100% correlated really adds value. It really decreases the amount of excess generation you have, and it decreases the amount of storage that you need. And so the conclusion is that when you're trying to integrate renewable energy using large, long-duration storage assets, you want multiple wind farms or multiple generation assets to be using a grid, and a storage asset to be leveling all of those combined generation assets variability versus trying to manage the output from a single wind farm. So where we are right now in our project, our primary project is called ASSIST, Alberta Saskatchewan Intertie and Storage Project. It's located near Lloydminster. We're in the early development stage. Being located in Lloydminster also allows us to be a virtual intertie between Saskatchewan and Alberta. The size of the project is 300 megawatts in generating capacity. In terms of duration, from a market analysis and a historical value perspective, we see the best size to be around 60 hours of storage. To put into perspective, this amount of power could supply Saskatoon for 3.5 to 4 days, or Red Deer for a week. This would be the first project of many, we hope, to utilize the same front-end engineering and design methodology. The rough CapEx is somewhere on the order of $700 million. Given that we're pre-FEED, there's a fair amount of uncertainty in that. Right now, we are out looking for money, roughly $5 million to firm up commercial support and complete the front-end engineering and design, with the expectation that we can build this asset in the next 3 to 4 years. So some of the hurdles in our way, in Alberta right now, energy storage of all types, if you are charging from the grid, you are paying the same charges as a load customer, an end-use customer. And then when you're discharging, you're paying as a generator. Now, paying it as a generator is fine, but paying as a load customer, the same as someone who wants power on uninterruptible basis, doesn't make sense, because a storage asset wants to be operating when electricity is in excess and the system is in excess, and therefore there should be an opportunity rate for storage within the market so that it can compete fairly with other generation sources. In Saskatchewan, we are progressing towards discussions with Sask Power and the government to really build up momentum behind the opportunity around compressed air energy storage so that we can gain some traction in Saskatchewan. Obviously, the market is larger in Alberta, but both provinces have phenomenal salt, geology, and wind generation opportunities. And so we expect one of these to go forward first, and that makes the Lloydminster location, again, very useful. And as I said, for ASSIST, we are working on funding for commercial support and FEED. So conclusions, I hope that hasn't been too fast, and I hope it's been interesting. Love to hear your questions, but in concluding, I think it's really important to know that in Western Canada, we can develop a project today that can meet loads demand 24/7, 365 using wind energy and compressed air energy storage that results in 80% lower emissions than a combined cycle gas turbine. And that would enable us to replace our coal fleet with renewable energy at a competitive cost. Western Canada is really ideally suited for compressed air energy storage due to our workforce, our proven geology, and our wind generation resource. We could build many of these projects while we are looking at one to start with. To get to this level of wind integration that we would require, we would need multiple assets of this type within the province, and there is suitable interconnection opportunities with the existing grid to do that today. And really the opportunity is on us collectively as a group of folks interested in progressing Western Canada's economic situation. This really allows us to take a leadership role in the burgeoning energy storage space, leveraging our significant and phenomenal experience in the oil and gas industry. So with that, I'll leave with you guys my contact information. If you can't copy this down fast enough, I recognize it's a long one. Just one of the moderators knows me quite well and can get you in touch with me. and looking forward to questions.
Hey, Robert, I've got one for you. Is my audio coming through all right?
Yes.
Yeah, okay. Hey, with the capital cost of a little over 700 million, where does the cost sit for developing the cavern versus facilities kind of topsides costs?
Very roughly, it's roughly like 10 to 15% of that is in the caverns. So you're looking at like 70 to $100 million to do the cavern development. What's really nice about the cavern development, while it's the longest lead component of the project, due to the time it takes to dissolve all this salt, it could be utilized for other purposes, whether that's natural gas waste disposal or hydrogen storage, should that be of interest. So there's multiple off-ramps for that facility, should you go down that route and then need to pull out of the compressed air facility.
And like all that solution mining is just sort of leveraging experience from the potash miners in Saskatchewan, basically, or
No.
I'm not super familiar. No, it's oil and gas.
Correct. Yeah. So there are large volumes of natural gas and LPG, bitumen that are stored in caverns all throughout the province. I think the first storage cavern for natural gas was actually developed in Saskatchewan in the 50s. You basically drill a hole down into the salt formation, you start injecting water and some blanket substance, and then you control the level within that cavity that you're building. As you inject more water, you control the level of where the water is to control the shape of the facility that you're building. It's far more complicated and complex than that to actually do it, I'm sure, but that from a very high level is how it's conceptually completed. And there's hundreds of these throughout the province that are being used for multiple different uses. A lot of them in the Fort Saskatchewan area and some in the Lloydminster area that are being used by the Husky upgrader for CHOPS waste separation.
I wonder if I could ask the question. I'm Stuart Middleton. I have some understanding of this technology. I've been a member of SMRI, the Solution Mining Research Institute, for some time. Sat through an awful lot of papers on this. One of the major concerns, and the reason that the Germans haven't gone beyond Hunter, is a concern for safety, for cavern integrity. Because, as you said, yes, we in Saskatchewan, where I live, we have lots of gas storage caverns that are developed. But the difference between what you're proposing and a gas storage cavern is the cycle rate, whereas they're cycling on months and you're cycling on hours. And that's a big concern in Germany. Now, in Germany, they would love to have the sort of capacity factors that you were talking about there, because their models have to go to deep discharge much more frequently than you were showing there. But I would like to have any comments you have on that.
Sure. So I think that the depth of the salt really matters. You might know more about this than me, but the creep rate within the salt changes as your depth and internal pressure of the cavern change. And the salts that Huntorf is in are quite a bit shallower, I believe, than the salts that we are looking at. So that is one difference. I know that when we look at Huntorf, I think it's got more like 16 hours of charge-discharge capability, and we're looking at 60 over 4 caverns. So they've got one big cavern that they're charging and discharging pretty rapidly, and we're looking at multiple caverns that we're moving more slowly. When you look at completely charging and discharging the asset, given that we have 60 hours of duration, we would only be near fully going through that discharge cycle once a year. So it's not, while on an hourly basis, you're probably pulling out and pushing air back in more than you would in a gas cavern, and definitely the volumetric flow rate and mass flow rate are way higher. I don't think that the pressure swings over a year would be that much different. Definitely need to spend a significant amount of engineering effort on the analysis of the salt that we're looking at in particular, and that will be a component for us to move on down the road. And part of that is the creep modeling through the exposure to these cycling events. But
That's very good. I wish you lots of luck.
thank you.
I have a quick question. This is Paras. Yeah, well, great presentation. Yeah, I noticed that your delivery, one of the tables, your price that you are assuming, or your model is assuming getting, is $89 per megawatt hour, which is the cheapest one, which assumes you are using natural gas, right?
Yeah.
Now, $89 is like, I often monitor the price, real time price, and it's often it is lower than that. So it's very very tight in that area, right? That project will make profit or not. Now, lately, the newer development is that generators are going to get paid to have that generation capacity. Did your model take into that potential payment for that, having that generation capacity? Let's say 300 megawatt near Lloydminster. Let's say if someone has a 100 megawatt wind turbine facility or wind turbine farm, they are going to get paid to have 100 megawatt generator, not one, multiple units. That generation capacity, earlier they were not getting payment. Now they are going to get payment. So if you have 300 megawatt of generation capacity, though intermittent, only for 60 hours, but you may be entitled for payment that will bring down your $89 lower. Did I make it clear?
I think so. So I'll try and address that in two ways. First question is, comparing this to the average pool price is not a fair comparison.
Okay.
When you look at the daily hourly pool price, and you see numbers like $30 a megawatt hour, in 2016 they were really low. 2016 they were like $23 a megawatt hour or something like that.
Yes.
NMAX built this massive thing called Shepherd. It flooded the market. We had oversupply all year.
Absolutely.
When you look at the value of the market, it's something like 50% of the value in the market is in less than 10% of the hours. And so looking at a levelized cost, which is what I'm looking at, and comparing that to an hourly number that you can go and pick up on any given hour, isn't a fair comparison, because I would be saying I can supply also those peak hours when prices are $999 for three or 4 days in the end of August. I can supply those or I am supplying those at 89. So while 89 is higher than I think what the average has been historically, that model also didn't account for ancillary services. It didn't account for excess value of the renewable. It didn't account for RECs. There's all these other things that aren't accounted for that would make it comparable on an operational basis.
Got you.
So we have run on more than 10 years of historical hourly pool price data, charging and discharging this asset without future knowledge, and the asset's able to produce an IRR in the range of 10 to 15%.
Okay.
So not in 2016. 2016 everybody got smoked, but thanks NMAX. You've reduced our power cost, I guess. So that's one side of it. One of the other things that you alluded to was or suggested was the benefit to renewable generators of having this sort of asset either locally so that you could actually build something there, or just on the grid in general. And so definitely having a storage asset locally would enable you to build a bigger wind farm with less transmission constraint. How that would work through the ISO right now, I don't know how. I think they would say the generation asset needs to be, where it's like a copper plate. We don't have nodal pricing. So they would suggest that you need to build a transmission line to connect all of your power to the main lines so you can get all of it to the market without constraint. Whether that's the right thing or not, that's a different discussion. There is, though, value that the storage asset provides when it's working in a merchant type model. It will uplift the prices when it is storing on a copper plate methodology, primarily when the prices are very low, when wind generation is all on. So wind generators get an innate benefit from storage being within the system that they are not paying for directly, should that storage asset move forward without a contract with them. And that is a real benefit that we're trying to monetize through contracts with wind generators, because obviously they're the ones who benefit a significant amount from that storing of energy and reducing excess during periods of high wind. I definitely agree with you. If you can use storage and build a smaller transmission line or utilize a smaller transmission line to build a bigger wind farm in the best places, that makes a ton of sense. I think that requires further discussion with the ISO to make that actually happen.
Okay, thanks, Robert. Can we go to Leo? Leo had his hand up. Go ahead, Leo.
I have two questions. Had a capacity market been adopted, would that have changed things?
A capacity market in general could have been good, but the capacity market that we ended up with was, I think Leo, do you know one of our former chairman, I think. So
yeah, I know Larry quite well, yes.
Yeah, so you're probably pretty familiar with the project, etc. So thanks for joining and
well, I had trouble logging in, so I missed all of your presentation. I'm sorry.
Well, that's okay. We can send it to you should you want it. But a capacity market, if it had long duration contracts, yes, it would help any generation facility enter the market. The way that the capacity market ended up was inefficient. It was providing a short-term capacity contract, which doesn't allow anyone any price certainty going out to a financier or someone saying, I've got a 3-year contract or a 1-year contract 3 years in the future for capacity. They're like, well, what about year 2? And so that was the problem with the capacity market in my mind.
Right. One more question, and I missed the first part. The two projects that have been operating for a long time, one is Macintosh, and I don't remember the name of the German one. But in relation to the caverns, what has been the experience that they have had with their storage caverns?
So my knowledge is about the Huntorf facility, which is the German facility. They have not had issues with the caverns. They've had some issues with the tubulars, and to my knowledge, they haven't had any issues with the caverns. They have had to replace the tubulars, and I think they replaced them or lined them with a a glass fiber composite, because this air entering the cavern is 100% humidity and it is warm. And then you're putting it into a salt environment. So corrosion is an issue. And so that needs to be seriously considered when you're looking at the metallurgy of the tubing string that you're putting in, or you put in some sort of maintenance plan or some sort of coating to deal with that. But to my knowledge, that's the issue that they've had. And I think they're using the same caverns today that they have since day one, and they're looking at building a second train is word on the street in the CAES community. So using the same caverns. So these caverns have a long life, as long as you don't wreck them and you have followed the CSA guideline for the proper operation, and I think you're good to go.
Okay, thanks, Robert. So we have a question on chat from Alan, who says, does the air have to be dried on re-emergence from the cavern as occurs with natural gas?
Does it have to be dried out?
Yeah, that's what the question says. Yes, does the air have to be dried as it comes out from the cavern? So on re-emergence, on the production side, do you have to dry the air before you can use it?
I think from a very high level, no. You would design the system so that going through the expander, you're not going to go through a freezing process. So you reheat the air enough that you don't have that issue. As you compress the air, a lot of water drops out. So air, when it becomes denser, it becomes less good at holding water. So you drop out a lot of water as you're going through, like a significant amount of water. Blew my mind. Significant amount of water drops out as you're compressing this thing, and you put it into the cavern. As it comes out, I would therefore expect the relative humidity of the air to be lower than, like, to be reducing as you expand it, provided it's got enough heat going into it. And therefore, I think icing would be less of an issue. I haven't seen anything that would suggest you would need to dry it. But I think it's a different rationale to why you would need to do that in a gas storage facility, is that you're picking up moisture from the salt, because there is water within the salt that is coming out as you move fluids throughout it.
Okay, thanks. So anybody else got any more questions? Anybody else questions? Yep, so Ivor. Go ahead, Ivor. You muted? You'll need to unmute yourself, Ivor.
They look unmuted. Interesting.
Ah. Okay, you look good now, Ivor. You should be able to ask a question.
Maybe type it in, maybe, if you can.
Yeah, put it into chat then if you can't, if your microphone's not working.
These are great questions. You're pushing my knowledge and giving me questions that I need to write down for later.
Okay, anybody else other than Ivor have a question? Yeah, Leo, go. You'll have to unmute yourself again, Leo.
The project that's planned for the southern United States, have you been following it?
The Apex case?
Right.
Yeah, we've spoken to them a few times. They got an investment from Siemens or from Dresser-Rand to develop the facility further and really showcase their technology. I haven't heard anything recently on updates. My understanding is that they're brining. So they're solution mining the caverns.
Oh, okay. Right.
Which is a long process, and but I expect to hear good news from them soon. And you know, obviously, wish them all the best, because I think a success in this space moves everybody forward.
Are you using the same equipment and process that they are?
Right now, in the model, what we're seeing is that the design that they're using, which is a Siemens, formerly Dresser-Rand technology, is the most cost competitive. What's interesting is, should we, some of the investors that we speak to want absolutely no carbon exposure. So they're large, mainly European multinationals. They are not allowed corporately to increase their carbon exposure, particularly when they look at developing things in other countries. And so in those scenarios, an adiabatic system makes a lot more sense. Whether they're contracting with us or providing funding for us, that would push us in that direction. When I look at it from a purely cost economics hat and 80-20 rule, diabatic case with the Siemens technology wins all day long. But if you really need to say I'm 100% renewable, we can do that. And maybe Google or someone who wants 100% renewable product 24/7, 365 says, yes, I need it to be 100% renewable. You can do it. That's the lowest price I can imagine. I haven't seen anything remotely close to that. So, then we would go with that technology.
Maybe one last question. The DTS problem, that's been there forever.
Yep. So he's talking about this double charging, or this charging the storage asset as a firm load customer. RMP has been working on this storage facility, trying to develop this storage facility for probably 8 years. One of the hurdles for it economically is this DTS rate that's being charged as a load, and it is a hurdle for any storage asset operating within the province if you're charging from the grid. Right now, the ISO is going through a tariff redesign. Again, there is an energy storage component to that discussion, and I'm very hopeful that we will see something develop out of that will enable energy storage to participate fairly within the market. There are people who see it as a load and want it to be charged as such, but I think there's now significant evidence that it is not the same. The fact that you can interrupt it at an instantaneous basis, that it's charging when prices are low, and would desire to reduce transmission costs to everyone, provided a price signal is effectively given. I do believe that we will see movement on that shortly.
Are the battery installations that are going in the province going to be charged to DTS as well?
Most of the ones that are currently going in are not drawing electricity from the grid.
Oh.
As far as I know, none of them are pulling from the grid. They're all co-located with a generation, so they're not going to be charged DTS.
Okay, thanks.
Okay. So any other questions? Anybody got a question?
Robert, it's Dave Ilse here. Can you give me an idea of what kind of support you're getting from government of Alberta and the government of Saskatchewan? And is there a shortfall? In other words, are you not getting support?
So I don't want to say that we're not getting support. We have received support from Alberta Innovates. We have received support from NRC IREP. So federally, we've received support. Financially, we've also received support through discussions with them. It's been very hard to elevate issues such as the DTS issue to the people in political realms that it needs to get to resolve it. We have not had support in that space under either NDP or Conservative or UCP governments. I think that definitely part of why we did this white paper and why we are trying to share this message is to get it out to as many people as possible to say, we have this awesome opportunity to really lead the world. And in a space that everybody wants to see someone lead in. And we can do it today without, spending billions of dollars on transitional training. And all we have to do is these little things and kind of get out of our own way. And I would love to have some more support in that space. It's very noisy, this space. So trying to get it heard, it's probably not that people aren't willing to listen. It's just a problem of, I hope it's a problem of getting our message heard above the other noise. And so this sort of white paper is trying to do that, to say, hey, look, we can do something great here. Let's try it. There's not a lot of risk. Is that answer your question?
That's what I was looking for. Thank you.
Good. So I think we should. Sorry, you had something, Leo?
There was a white paper mentioned.
Yeah. There's it's on our website. It's RMP Energy Storage.
Okay. Very good.
Or RockyMountainPower.ca still gets you there. And it's on our website. But I'm happy to share it with the moderators here, and they can forward it on directly should people want it that way as well.
Thank you.
Okay, thanks. So I think we should draw to a close. We've kept Robert way longer than we originally promised.
That's great.
We'd like to thank you, Robert, very, very much for a really interesting presentation, and really have explained very well indeed what can be done with this technology. And we wish you all the very best in getting it going. And we want to see Alberta doing what you've predicted there by 2030. So thank you very much. And thank you to all the audience and the questions that have come through. As Alan says, great stuff, and someone else, great presentation. There's lots of messages coming through. So we really appreciate your time, Robert. Thank you so much.
Yeah, thank you all as well. I appreciate it.